This is torsional pendulum. In this type of pendulum, a metallic disc or cylinder is suspended by a thin metallic wire or nylon wire. When this disc is twisted and released, then it rotates both clockwise and anticlockwise directions. In this torsional pendulum, we have rigid support, nylon or metallic wire by which the disc is suspended, and rotating disc. It is a metallic disc. It can rotate both in clockwise as well as anti-clockwise directions. The disc can be twisted by using external force. Suppose we are doing the experiment in our lab, then we can just twist the disc by using our hands as shown in the figure. Suppose the disc is twisted in anti-clockwise direction and released, then the disc performs rotational motion in clockwise direction. Implies the disc rotation is opposite to the direction of twisting force. Here we have applied twisting force in clockwise direction, and suppose this twisting force is released. That means we stop applying the twisting force by our hand. We remove our hand. After removing our hand, the disc starts rotating on its own. So after removal of twisting force, the disc moves in the anti-clockwise direction. Repeat once again. We had applied the force on the disc in clockwise direction. After removal of the twisting force, the disc started rotating on its own in anti-clockwise direction. And thus, if we stop twisting the disc, then what happens? After removal of the twisting force, the disc starts rotating on its own. It will perform its rotation both in clockwise direction as well as anti-clockwise direction. So it keep on repeating clockwise rotation as well as anti-clockwise rotation. What is observation? The observation is sometime the disc is moving in clockwise direction and some other time it is moving in the anti-clockwise direction. So it is repeating its motion, and whenever something is repeated its motion, then we call it as an oscillation. So this disc, after removal of the twisting force, it is performing its rotation both in clockwise as well as anti-clockwise direction. And so this is the condition. We say the disc is performing rotational oscillation about its axis. What is the axis? The axis is nothing but suspended string, suspended metallic wire. So that is the axis of rotation. So the disc is rotating about the axis of rotation and performing both clockwise as well as anti-clockwise motion, and it's a rotational motion. Therefore we can say rotational oscillation. This type of rotational motion in which a body performs repetitive partly clockwise rotational motion and partly anti-clockwise rotational motion is called as angular oscillations or torsional oscillations. Now the next question is, why disc performing rotational oscillations? We came to know that disc is already performing rotational oscillations, but why? So the answer is because of the restoring torque produced in the wire, and this restoring torque depends upon the angular displacement. More the angular displacement, more the restoring torque will be produced in the wire. So because of this, the disc is performing rotational oscillations, and the direction of this torque, restoring torque, is opposite to angular displacement. In figure, theta standing for angular displacement. More the angular displacement, more the torque, and direction of the restoring torque always opposite to angular displacement. These both conditions are nothing but conditions of simple harmonic motion. In more simplified form, we can call it as an angular S.H.M, angular simple harmonic motion. What are the reasons? The first reason, because the disc performing to and fro motion, moving forward and backward again and again. That is the first reason to call it as angular S.H.M. Second reason, restoring torque directly proportional to angular displacement. This is the second reason. And the third reason, the torque, the direction of the torque vector is opposite in direction of the angular displacement. This is the third one. So these three conditions are satisfied, in case of rotational oscillation of this disk. Therefore, the disk, we can say, performing angular S.H.M. So torque is directly proportional to negative of angular displacement. Why? Because torque is directed in opposite direction of angular displacement. Therefore, we take negative symbol here. So tau is proportional to negative theta. Now constant of proportionality C. So tau equals to minus C theta. What is C? C is equal to tau divided by theta. Tau is nothing but torque and theta nothing but angular displacement. And negative sign stand for opposite direction. The magnitude of C is equals to tau divided by theta. Therefore, C is nothing but restoring torque per unit displacement. But tau is also equals to I alpha. I nothing but moment of inertia of the disk, and alpha is the angular acceleration. So this is equals to I multiplied by d2 theta by dt square. So tau equals to minus C theta, call it equation 1, and tau equals to I d2 theta by dt square, call it 2. Now from 1 and 2, we have I d2 theta by dt square equals to minus C theta. This can be written as I d2 theta by dt square plus C theta equals to 0. This is nothing but differential equation of angular S.H.M. This equation can also be written as I d2 theta by dt square equals to minus C theta, and d2 theta by dt square I already told you alpha. So alpha equals to minus C divided by I theta implies alpha proportional to minus theta, because C and I are constants, implies angular acceleration directly proportional to angular displacement, and angular acceleration is opposite to angular displacement, opposite in direction of angular displacement. Therefore, so we can say disk is performing angular S.H.M. indirectly. Torsional oscillations, nothing but angular S.H.M. Finally, let us define angular S.H.M. Here, this disk performing to and fro motion. It is moving forward as well as backward. So it is moving to forward as well as backward, that is to and forth motion. And it is a rotational motion. And there is a torque involved in this motion. And this torque depends upon angular displacement. More the angular displacement, more the Therefore, the motion of this disk we can consider as angular S.H.M.